They closed. Yeah, that's right. Thank you. Good morning. Today what we do is we first finish the proof of Cardy's formula, which we almost finished last time, and then we discuss a similar result for the Ising model spin correlation. Okay, so let me just remind you where we are for the Cardy's formula. So we have fixed a domain omega with 3 marked points A, B, C. We have discretized it by hexagons of size delta. We have considered 3 events: QA delta, or Q0 delta. So A equals 0, B equals 1, and C equals 2 whenever it's more convenient. So Q0 of delta of Z is the event that A and Z, point in the bulk, are separated from B and C by a black path. Q1 delta and Q2 delta are defined analogously. By replacing A by B, the role of B by the role of A by the role of B, and the role of A by the role of C in the definition of both. And H0 delta of Z is simply the probability of Q0 delta Z, and you define H1 delta and H2 delta analogously. Okay, so what we did last time was we first stated a theorem about the convergence of the following linear combinations: H0 delta Z plus E minus E2 pi I over 3 H1 delta Z plus E minus 2 pi I over 3 H2 delta Z converged to some conformal map, and that H0 plus H1 plus H2 converge to 1 as delta goes to 0. So we explained why this is implies the crossing probability conformal invariance. And what we did last time was we obtained some precompactness estimates that allowed us to pass to limits along subsequences. And we explained why the boundary conditions were doing the right thing, meaning that the boundary of the domain by the limit of any limit of this family is a homomorphism that sends the boundary to an equilateral triangle. Well, it's an exercise to check that the boundary conditions here are the right ones. The proof is exactly the one we used to prove the result for the complex linear combination. So what is left is to prove that the limits are analytic functions. Holomorphicity or analyticity. And we did a key step last time, which was a discrete version of the Cauchy-Riemann equation. And the way it was phrased was as follows. It was an identity relating discrete half derivatives of functions around a vertex. I'm going to explain again what this means. situation was as follows. You have an edge here, you have another edge here, and another edge here, all of which are part of a hexagonal lattice. And the result was that a discrete analog of the discrete derivative of h0 delta is the same as the discrete derivative in another direction of h1 delta, and the discrete derivative in yet another direction of h2 delta. So what are these analogs of discrete derivatives? Well, we define for an edge E going from a vertex x to y, an oriented edge. We define the discrete positive part of the derivative of the function h0 delta as the probability that the corresponding event occurs at y but doesn't occur at x. Okay. Similarly, for del E H1 delta del E H2 delta, and we define the negative part as the event with x and y exchanged. Q0 delta at x minus Q0 delta at y. Okay, this way, minus. Okay, so this way, what we have is that the discrete derivative of a function like h0 delta is going to be the difference between the positive part and the negative part. Okay, because here we are computing by definition a difference of two probabilities, and the difference of two probabilities can easily be seen to be the difference of the probabilities of the subtracted events. Okay. Well, and one last remark. It's going to be useful. It's very easy, but DE plus, whenever whenever it is valid, this definition, DE plus is the same as D minus E minus, where E minus E is the edge that goes from y to x. Okay, so we have not quite obtained an identity between discrete differences here. We have merely obtained an identity between somehow half of the derivative. So now we need to explain why this still is strong enough to imply that these limits are analytic. Is it clear? So, if we think for a minute, we see that we certainly don't have enough regularity to assume that the limits are differentiable. So how can we possibly prove discrete Cauchy-Riemann equations on the limit if we don't know the limits are differentiable? Well, the idea is that we can instead use an integral criterion for deciding about holomorphicity. So that's the Maurer-Rask criterion. So if a continuous function from a domain of the complex plane that's complex valued is such that any contour gamma contained in the domain, we have that the contour integral along that contour of the function, so the complex contour integral is 0, then F is holomorphic. So, because you might have seen that result at some point in your studies, let me just say a few words about how it works. If you have seen it, you will remember, and if you haven't seen it, you should look somewhere. So the idea is that if you have that discrete criterion, you can actually define a primitive or antiderivative of the function in a consistent manner. And whenever you can define a complex antiderivative of a function, it means this complex antiderivative is differentiable and has the original function as derivative. So you define the primitive antiderivative of this function. It is complex differentiable, so it is holomorphic, and we know that holomorphic functions are infinitely differentiable, and that their derivatives are all holomorphic, so we obtain that the function is holomorphic. That's how it works. Yeah. Now we would like to make use of that criterion. So now we want to use that criterion. And so how are we going to use it? Well, we are going to try to compute a contour integral of a limit of this function. So, but first, we say that, okay, we want to make use of this criterion, but in the end of the day, what we know about our function is this identity. So, we would like to rephrase this criterion in terms of some quantity involving discrete derivatives. So, let's state a lemma. If f is an alpha continuous Hölder function, then its contour integral along any contour, gamma. Well, let's say that gamma is the boundary of a bigger domain. No, a smaller domain. Capital gamma. Okay? Little gamma is a curve, that's the boundary of the domain. So the contour integral of the function here is going to be square root of 3 over 2i times the sum over all the edges, all the oriented edges in the discretization of this domain. So by Honeycomb. Of what? Of complex edge, I mean an edge viewed as a complex number, I'll explain what it means, times discrete derivative of the function. So where the edge is viewed as the complex number, so the edge is xy, it is viewed as a complex number y minus x, and the EF is f of y minus f of x. Of course, that's not exactly true, so there's an error term. It's a big O of delta to the power alpha. Yeah. So it means that we can approach a contour integral by a discrete sum, which is like a surface integral. Let me make a remark. This is analog of a standard version of a Green-Riemann, which says that the contour integral of a function along the boundary of a domain is equal to 1 over 2i times the surface integral on the domain of the function. d bar, where d bar is 1/2 x derivative plus 1/2 y derivative. Okay? So the idea is that we translate a contour integral into a surface integral, and we further discretize the surface integral in this manner. Okay? So somehow this quantity is an analog of that. Modulo the square root of 3, it's an analog of that. Okay? Is it more or less clear? I need to prove this lemma, but is it clear what the lemma means? It means we can approximate a contour integral of any Hilbert function by a discrete surface sum over all the oriented edges of the discretized surface of the value of the edge viewed as a complex number, the difference of the value of the endpoints, times the discrete derivative. Okay. So how do you prove that? It's fairly elementary. So the first thing is you discretize the surface, the contour integral as a discrete path integral. Okay, so we go back to the basics. What is a complex? What is a a complex contour integral? Well, we can approach it by Riemann sums if the function is continuous, and so this is the same as the sum over all edges along the path that are counterclockwise oriented. I mean, contour integrals are always counterclockwise oriented. So you discretize your path by a path of edges of the honeycomb lattice. Okay, that becomes your path. It's a finite collection of edges. And what do you sum? Well, you sum the value of the function at the endpoint. So let's call the edge xy as usual. So if we take the average value of the function at both endpoints of the edge times what the edge should be, so just y minus x. Okay, plus a small error. Okay, so that's really just saying that our contour integral can be approximated by a Riemann sum. Now, the idea is that you want to make this become a surface integral. So what do you do? Well, the idea is that you can decompose this contour integral into a sum of many, many contour integrals. So it's going to be made of a sum of the faces of gamma delta. So you're going to sum over all the hexagonal faces contained inside of the contour. You're going to sum over all the edges of that face when you orient that face counterclockwise. F of x plus f of y over 2 times y minus x plus the same error. So that's a very simple combinatorial identity. What happens is that here you sum over many more edges. Previously, you were only summing over the counterclockwise oriented edges of the boundary of this gamma delta, which was the little gamma delta. Okay? Now you're summing over all the edges that are inside, essentially. First, you're summing over all the faces, and then you're doing a contour integral along each of these faces. So what happens is that inner contributions cancel, leaving only the boundary contributions that appear here. The reason is that an inner edge, an edge that is not on the boundary, appears twice in the sum, for it is the boundary of two faces. And for both faces, you will have the same contribution here, but the sign will be different, for the edge will be oriented counterclockwise with respect to both faces to which it belongs. So in two opposite directions for all the edges that are inside. So we have this simple identity. Now we can rewrite this by using another identity. So now for any face what we have is that this thing we were summing, so sum over xy of the face counterclockwise oriented, so it's a sum over 6 edges counterclockwise oriented of well, f of x plus f of y over 2 times y minus x. This sum can be just rewritten in a simple manner as, you know, that looks like integration by part. So that's the derivative of the identity function, and that's a function. And so you would like to rewrite this in terms of the identity function times the derivative of the f function. So that's exactly what you end up doing. So what you end up with is this quantity, f of y minus f of x times x plus y over 2. Okay. So it's a complete analog of discrete integration by part. And of course, if you have a discrete integration by part, you should not forget that you have a minus sign. Okay. So let me make the remark. It's the same as saying that u dv is minus v du if there are no boundary terms. Well, let's say on a contour of okay. A closed integral satisfies always this. So so that's okay, that's an exercise. It's not particularly difficult. There is no surprise. It's, if you know Abel resummation, it's exactly Abel resummation. You have just 6 terms in this sum, and you need to check that these 6 terms are equal to these 6 terms in this case. Okay. So from there, where do we go? So from there, so we can rewrite this a little bit. Sum over the faces sum xy of the face counterclockwise of well, let's write with the convenient notation the derivative of f times dh. Yeah. Not dx, x plus y over 2. So now what we see is that we would like, in principle, to say, well, this is going to be, you know, nice, and that's something we can say is this analog of a surface integral. Except that the terms, some terms here are not of the right scale. This x plus y over 2, we don't really like it this way, because you know, well, you know, the size of this guy is macroscopic, and that doesn't really look good if we want to make a surface integral. If we want to make a surface integral, our summand should be of order delta squared. That's only of order delta because that's the difference of the values of the function at two nearby points. At least that's what we would hope it is in the end of the day, but that's of order 1. So that's not really good for a double sum. So we need to change things a little bit. And the idea is that we can just subtract the center of the face here. Doesn't change anything. Why? Because if you have the center of the face, if you just expand this product, the center of the face factor of this sum is 0. Because here, if you take the center of the face out and you sum over, you just sum all the differences of the values of the function on a closed contour. So you end up summing 0. So you can add this without any modification and leave it there. So that's better, because now the center of the face minus this is of order delta also. So here we have something of the right order of magnitude. So now this, what is this? Well, we have a hexagon, and we are comparing x plus y over 2, which is the center of edge, to a center of the face. And that's this guy. Well, I should have put a minus here, as I said. There's a minus here, sorry. So what is this? Well, this is simply, if I remove the minus from there, well, no, I should leave the minus here, but this is simply I times square root of 3 over 2 times y minus x. This is x, this is y. So this is dual edge. So it's I times y minus, it's I times y minus x, and I take the half of it. So it's a simple exercise to check this, okay? And so in the end of the day, I obtain exactly what I needed. I've forgotten the big O, and I get just the sum over the faces of I times square root of 3 over 2 times y minus. Well, I should rewrite it somewhere down. So I get 1 over 2i square root of the sum over the faces so 1 over i's sum of the over the faces. Sorry for this thing. Del sum over the edge of the face of okay, the midpoint of the face. Okay, sorry, it's very simple. I'm just rewriting what I wrote. So I should get D, E, F times E. Okay. And now what I'm doing, I'm summing over all the faces, I'm summing over all the edges in the counterclockwise orientation of the faces. So in the end of the day, I can just rewrite this as a sum over all the edges inside. All the oriented edges inside of the quantity I want. Just del E F times E with the square root of 3 over 2. Okay? Well, this identity is true, and the calculations are very elementary, and we explain all the ideas, so that's what we... Okay? So consider proof of this lemma done, unless there are other questions. Okay? Yeah?
It's half easier than I did.
Yes, because I cheated a bit. I mean, But you know, that's a very this identity is true, and the reasoning is true. Okay. Yeah. So the idea is that I said there was a 1/2 in this difference, but actually this center of edge cancels, and the only thing that's left is a difference of opposite centers of faces, which brings you an extra 2. And then when you sum over all the possible orientations of all the edges, you get a you get to divide by 2 if you want the sum to be correct. Okay. It doesn't really matter in the sense that we want this to be 0 in the end. So you know, it's totally fine to have small constant mistakes, but I'm almost sure that this is correct. I mean, written as such is correct. Okay. So now what do we do with that? One last step and we are done. So we need to evaluate the contour integral of the limit of this function using this identity. So we're just going to rewrite that the contour integral up to a small error is going to be given by a sum, and we will compute this sum and plug in the identity we have. So let h be the limit as some sequence delta n goes to 0 of h0 delta n plus e to pi I over 3 h1 delta n plus e minus 2 pi I over 3 h2 delta n. Okay? So we want to show that this contour integral, the contour integral of this guy is 0. So fix gamma, which is the boundary of a big gamma, and let's say that, okay, the contour integral along gamma of h is approximately equal up to an error that vanishes as delta goes to 0 to the following sum over all edges inside the discretization of is equal to up to constant. We don't want to care about the constant because it's going to be 0. So the sum over simply E times del E H, which we're going to rewrite as a sum over all the oriented edges of the graph of E times del E plus H0 plus E to pi I over 3 del E plus H1 plus E to 4 pi over 3 del E plus H2. Okay? So how did I obtain this? Well, you know, obviously this H is by definition H0 plus E to pi I over 3 H1 plus E 4 pi I over 3 H2. The small trick is that I added the plus here at the expense of adding a 2 there. How did I do that? Well, the idea is that here I'm summing over all the edges of the graph, okay? And in order to obtain a discrete derivative at a given edge, what I need to do is I need to compute dE plus and subtract dE minus, okay? Except that since I sum over all the directions, the dE plus of one direction here is the dE minus of the other direction. And you can check that if you multiply things by the edges, then you actually can just rewrite it in this way. I mean, basically, this is made of a dE plus minus dE minus But since the d minus will be taken care by the d plus of the opposite edge, which will come with an opposite sign, you'll be fine. Okay? So that's exact identity. Now we are really almost done. So what we can write is, okay, we can split this sum into 3 pieces. So 2 times the sum of all the e's, I'm not going to write the gamma delta anymore, of e del e plus h0 plus the e to the 2 pi I over 3, the sum over all the edges of e times del e plus of h1 plus e to the 4 pi I over 3, sum over the edges of e times del e plus of h2. Okay. So now we really want to use this discrete Cauchy-Riemann identity, which relates the derivatives of h1 in one direction to the derivatives of h0 in another direction, and same for the discrete derivatives of h2. So the idea is that, okay, we can say this is simply the derivative of h0, but in a rotated direction. Okay? So let me write that. The first board. So we leave the first sum as such. This over 2, say, to get rid of the 2. This plus. Now I'm just going to do a small thing. I'm going to say, okay, this is edge over e to the 2 pi I over 3 of h0 again, plus the sum over the edges, and there's e 2 pi I over 3, e 4 pi I over 3, sum over the edges of e times the e divided by e 4 pi I over 3 plus h0, where e over e to the 2 pi I over 3 is the edge e rotated by 120 degrees clockwise around the origin. Okay? So I just exploited the identity here. I said, okay, if I take the derivative in this direction of h1, it's the same as taking the derivative in the direction rotated by 120 degrees clockwise of h0, and same for h2. That's exactly what I did. Okay? Now I just need to resum a bit to have the same term here, and I'll be done. And it will be exactly 0. So now we have that this is going to be sum over all the edges. So I'm just going to change the indices somehow. And I should be careful with the boundary, but the boundary doesn't have too many edges, so I'll be fine. So I just want to change the indices of summation. And I'm going to obtain, as I want dE plus of h0, factor of, while taking this into account and that these things into account, I will get 1 plus e 4 pi I over 3 plus e 2 pi I over 3 plus a small error. These are terms that could not be resummed over. Okay, so on the boundary there are edges such that if I rotated them by 120 degrees, they are now outside of the domain. So I have some small errors, but most of the sum is here. And so this is equal to 0 because we're just looking at the center of gravity of this equilateral triangle, and so that's identically equal to 0. So proving that the limit of h1 plus h0 plus h1 plus h2 is analytic is the same. You will do exactly the same calculation. You just don't have these coefficients here, but you end up summing something which is exactly going to be 0 for the same reason. Okay? So that somehow concludes, I hope at least I convinced you, about the analyticity. Okay? So again, we had a nice combinatorial identity. We needed to make it really become something useful in the scaling limit. The way we did that was we used Morera's criterion, saying that the limit would be holomorphic if the contour integral were 0. And we approximated the contour integrals by discrete contour sum. And then we used the discrete analog of a Green-Riemann identity to rewrite this as a surface sum. This surface sum, we had to manipulate it a little bit, but after a little bit of effort, it was able to spit out the terms for which we had an identity. So now we could plug in the identity we had, and at least for the terms in the bulk, we could just use the identity to resum and obtain 0. That's it. Okay? Questions? Yeah.
I'm a little confused by the notation.
Yeah, sure.
So your script h is the limit if delta goes to 0.
Okay, yes. So, well, we can add deltas here. But that's a good question. So yeah, I mean, we want to compute the integral of the limit.
But you use the discrete identity and then take the...
Yeah, so that's right. So we want to compute the integral of the limit, and the way we do that is by expressing it as a sum over the discrete functions that converge to the limit. We can do that because you have uniform convergence. And indeed, that's a point I was a bit floppy about. Yeah. Yeah. So I should put deltas everywhere to be precise. That's right. Absolutely. Thanks. Okay. So that concludes the analyticity. So now let's just conclude about the proof. Where are we? What have we proven, etc. So conclusion. We have shown 1, precompactness, 2, boundary conditions, and 3, analyticity. Okay. So with these 3 ingredients, we can conclude. So how does it work? So any limit along subsequences will satisfy 2 and 3. So now we need uniqueness. So we need that the solution to 2 and 3 is unique. Okay. So why is there only one holomorphic function that sends the boundary to the boundary, and that is analytic inside. So this is called the argument. So it follows from the argument principle. That's a result of complex analysis. Well, it precisely says this. If you map the boundary to the boundary and you make just one loop, one turn along the boundary as you turn along the original boundary, then you're bijective, holomorphic, so you're conformal. And there is only one conformal map that sends the domain omega ABC to the equilateral triangle. So, you know, somehow that's an exercise, but if you want to convince yourself of this, and you want something fairly visual, I think the simplest is to say, okay, let's just understand what happens in the case of the half plane. Understand this. The half plane. So you have the half plane here, and you have a map from the half plane to the half plane that sends the boundary to the boundary. That's increasing as you move along the boundary. The function increases. That's exactly, you know, this monotonicity we proved for the boundary conditions. So as you move along the boundary in the counterclockwise direction, you move along the boundary in counterclockwise direction. So why does it allow us to say that the map is, say here, a multiple of the identity? Well, the idea is that, well, along the boundary, the map is clearly increasing. I mean, that's by assumption. So now, if you look at how the real part of the map evolves as you move on the line that's above the boundary, it also increases monotonically, because the real part is a harmonic function, and the boundary condition is increasing. So as you move along the boundary, you increase. Okay? So when you move in this direction, you move in that direction. Now by Cauchy-Riemann equation, when you move in this direction, you move in that direction, because the derivative in the y direction of the imaginary part is the derivative in the x direction of the real part, which is positive. So basically, you can convince yourself that you have to be bijective. So if you map the half plane holomorphically onto itself in a bijective manner, you just a conformal map of the half plane, and then you're fine. Okay. So somehow it's an overkill to do it on the half plane and then invoke, say, Riemann mapping theorem to say, well, you can reduce your situation to a situation of the half plane. But I think that's a fairly visual and simple way to understand what happens. Okay? Okay. So so by uniqueness, we have convergence, not along subsequences, and this concludes the proof. Okay. So I was a bit quick on some details, but I hope you have an idea of the proof in the sense that there was no detail that is smart that was hidden to you. Okay. Okay. So now I want to speak about the Ising model. Okay. Any questions about percolation? So about Ising model. So let me just remind quickly what this is. So we have spins plus minus 1 that are living on a graph. Probability of a spin configuration. Yeah, I defined it on the first lecture, but I'm just going to rewrite quickly. The probability of a spin configuration is proportional to exponential of minus beta h of sigma. H of sigma, the energy of the configuration, is the sum over all the pairs of adjacent spins of minus the product of the spins beta is a positive parameter, inverse temperature. So you favor local ordering of the spins. And what we look at in this class is the Ising model on the square grid. So I'll explain what I mean by that. At the critical temperature, basically at the value of beta that sees a scaling limit. So we are going to take a square lattice like that. Okay? I'm going to rotate it by 45 degrees for convenience. We will have spins that will live on the faces, okay? That's again for convenience. Usually you make them live on the vertices, but it's obviously the same. Okay? So what we discussed on the first lecture is that for the square lattice, Ising model, there is a phase transition at beta critical, at the critical value of beta, which is 1/2 of log of square root of 2 plus 1. So what does it mean? So if you take a domain and you discretize it by finding square grid of mesh size delta, now delta is going to be half the size of a square for whatever will matter. And say you take plus boundary conditions, so you make the, you say that the spins on the boundary are plus. And okay, you ask the question, now you look at your Ising model on this discretized domain with plus boundary condition, and you ask the question, okay, let's take a point A here. What is the expected value of a spin at A in the bulk as delta goes to 0? And so the answer is that as delta goes to 0, this goes to 0 if beta is smaller than beta critical, and this goes to a quantity m of beta if beta is greater than beta critical. Okay, so which is positive. So now the most interesting thing is what happens at beta critical. Okay, and so the goal of this lecture and the next one is to explain something interesting happening at beta critical. So goal of the lectures, understand some features of beta critical, and the result I want to prove is the following. So okay, I want to ask the question, okay, you tend to 0 at beta critical. That's a result of Gonzaga. But how fast? How does it depend on the shape of the domain? Okay. Well, here's the answer. So if you take a constant of a delta to the power 1/8, and you take this quantity, you make it pass to the limit, then you converge to a quantity which I'm going to write sigma a omega plus, where sigma a omega plus is phi prime a, where phi is the unique conformal mapping to the power 1/8, and phi is the unique conformal mapping that sends omega to the unit disk. That sends a to 0, and that has positive derivative at it. So conformal mappings have 3 degrees of freedom. This fixes 2 and this fixes 1. So the phi is unique, and that's the quantity we obtain. So you see something that will blow up as you approach the boundary to the power 1/8 to the distance to the boundary, and something that depends explicitly on the domain, on the point, etc. Okay. So well, you have generalization of these results to more points, which allow you to say that actually the spin field once we normalize, converges to a continuous random field, which is not the Gaussian free field, it's a different field. Let me just mention some results of this flavor. Similarly, should give an idea of what happens. For instance, if you take two spins, a spin at A and a spin at B, and you look at c squared over delta to the power 1/4, the expectation of sigma A, sigma B, this converges to a continuous quantity as before, which can be computed explicitly, and it's sigma A omega plus, sigma A B omega plus, the one-point functions, divided by 1 minus exponential of minus 2 d omega AB to the power 1/4, and d omega AB is the hyperbolic distance between A and B. Okay. If you take free boundary conditions, so you don't force the spins to be free plus on the boundary, for the one-point function you will get 0 because by symmetry the spin has as many chances to be plus as minus, so it's not so interesting. So, but if you take the two-point function, for instance, you have a similar formula. C squared over delta to the power 1/4 converges to an explicit quantity, which is not the same as this one. The denominator is a little different. So a result which will be useful for us later, I want to quote here. So it's what happens with mixed boundary conditions, plus minus. Okay, that's important because we want to study SOD. Okay, so similarly, also, so now you know if you take plus minus boundary condition, you change half of the boundary, you want to have minus boundary conditions. What we have is that c over delta to the power 1/8 of the one-point function with plus minus boundary condition of the spin. That will converge to sigma A omega plus minus, which will be sigma A omega plus times the cosine of what? Cosine of pi times the harmonic measure of A viewed from A of the arc minus. Okay. Harmonic measure of the minus arc viewed from A. Okay. So the chance the Brownian motion starting from A exits the domain on the minus arc. So if there is no minus arc, this is just cosine of 0, it's just 1. If everything is minus, this just becomes minus the one-point function as it should. And okay, as explicit as you want to be. So obviously that part is also conformal invariant because the Brownian motion, as Vincent explained, is conformal invariant. Okay, so I don't have so much time today to give a proof of this theorem, but let me just give a statement we will want to prove next time. We'll spend all the lecture proving it. So it's essentially this statement, a bit slightly weaker, but it should explain most of what happens. So, statement we will prove So yeah, I should cite people. So this is results of myself with Dimash Alkak and Konstantin Izura. So statement we will prove the following. We are going to ask how the expectation of one spin at a point differs from the expectation of the neighbor. Okay. So we are going to look at the following quantity. So if this is A plus 2 delta with my notation. Okay. So it's the spin 2 lattice steps away from the original spin. Now we fix our domain, we choose our points, and we ask the question, okay, can we compare this quantity to that quantity? And so how should that behave? Well, at first order, this should behave like 1. There is no reason why the spin at a point, the spin at the neighbor should be that different. So to see anything interesting, we'll need to subtract 1. And now we get something more interesting. So we need to renormalize by the mesh size to power 1. And what we will prove is that this converges to what? To the discrete, no, not the discrete, the continuous derivative of the log of this 1-point function at x equals 0. Okay. So this will be what we will prove. And why is it going to be useful for our results? So let me just conclude with that. It will be useful to show that in general, for any 2 points in the domain, if you take the expectation of the spin at A, and you divide with the expectation of the spin at B, this converges as sigma A omega plus divided by sigma B omega plus. So we will not quite get this result. We will get this result with ratios, which conveniently avoids me from obtaining this normalization. I mean, I don't need to obtain this normalization to prove that result. That's getting rid of one difficulty, and that's really the way we do it in the proof. We don't know a priori this. We'll obtain this a posteriori, this coefficient. So the first thing we do is we take ratios of spin correlations at different locations in the same domain with the same boundary condition. So why will it allow us to show, I'm almost done, why will it allow us to show the result? Question? Well, it's very simple. How? Take the log. So we want to show that the log of the ratio converges to the log of this ratio. So the log of the ratio is, of course, the difference of the logs. And, okay, how are we going to compute this difference of the log? We are going to make just a sum with cancelling terms. The idea is that, okay, if I want to compute the log of the spin at A minus the log of the spin at B, what do? I take the log of the spin at A minus the log of the spin here, plus the log of the spin here minus the log of the spin there, plus the log of the spin here minus the log of the spin there, etc. All the inner terms cancel. And now the log of the spin at one point minus the log of the spin at the neighbor is exactly given by this. Because if I Taylor expand the log, the term I obtain is this. So it's going to be a sum over a path of log of the spin at one point minus the spin at the neighbor. Okay, so you sum over xy minus the log of the expectation of the spin here, and this will behave like delta, the delta times the derivative of the log of the spin, because we have precisely proven that this ratio -1 behaves like delta times this, and so it's easy to check by Taylor expansion that this difference is the same as this difference at first order. Okay, so you end up having something that converges to the integral of the d log, which is precisely what you should obtain is the difference of the logs. Okay, so that's it. Questions? Okay, so one last time. Next time what we prove is that this converges to that, where that is the derivative of the conformal map, the power 1/8. Okay? Thank you.